In 2.3, we begin looking at solving linear equations, and more specifically, we're going to be solving first-order linear differential equations. So the first couple of problems that we're going to look at are going to be just trying to classify whether a differential equation is separable, like we dealt with in the previous section, linear, like we're going to deal with here, or does it fit in both categories? Or does it fit in neither of the categories? So by the time we get to the end of this section, if a differential equation is separable, we have already been able to solve that. If it's linear, that's going to be something new we can solve. But if it doesn't fall into either category, then solving that may be something we're going to do in the future. So let's refresh our memory of what it takes to be linear. We need to recall that for this differential equation, t is the independent variable and x is the dependent variable. So if we have a differential equation where we have our differential and we could have some function out front or some coefficient that is a function of our independent variable, and if our differential is, or our dependent variable is x, then we could have x in the next term, and we could have another function of our independent variable. And then on the other side, we could have a function of our independent variable. And you may recall that our independent variables can come in different powers, but our dependent variables all have to be linear. Whether we have a first degree or first order, second order, third order derivative, that derivative has to be to the first power. Also, since x is our dependent variable, we can't have an x and a dx in the same term. And here we have an x that has to be to the first power. We can't have another x in there. So in a sense, that's to the first power, that's to the first power. All of our x's are on the left side, but we have our differential with respect to t. We have coefficients that are functions of t's, and on the other side, we can have something that's a function of t. And if that's the case, then it's linear. But if we throw in any other exponents here or here, we could have higher order derivatives as long as they're not raised to powers, or as long as there's not also an x in the same term as your derivative. But if that happens, that we have a mixture of x and its derivatives, then it's not going to be linear. So if we take a look at this one, notice that on the right side, we have a function of x. In order to be linear, we have to have derivatives of our dependent variable. We have to have our dependent variable. Everything else has to be functions of t. Since we have a function of e to the x here, then that is not linear. Any coefficient or the other side has to be a function of the independent variable, not the dependent variable. So at this point, we know this one is not linear. So we need to see, is it separable? So in order to be separable, and let's write the equation down here again. Well, let's go ahead and get dx dt by itself. So if we get dx dt by itself, then on the other side we would have e to the x minus x times t. So remember, to be separable, if we have our derivative on one side, the other side has to be able to be separated into a factor that is just one variable and a factor that's the other variable. And we can't do that. Here we're not able to factor out an x. This x in the exponent can't just be brought down front. So we have x's in this term and x's in that term, but they're not able to be factored out. We have an x and a t in here, So while this doesn't factor, that means that whole thing is one factor. If we only have one factor and it has both variables in it, then it's not separable. So in this case, it's neither separable or linear. All right, let's do the same thing for here. Let's see if it's separable, if it's linear, if it's neither or both. So this time, let's begin with separable. So if we get dy over dx by itself, we would move the 7y to the other side. So we would have 5xy minus 7y, and we would have to divide both sides by that parenthesis. So we would end up with dy dx equals that. So if we can get this factored where we have something that's a function of x, something that's a function of y, or we could have a constant, just as long as when it's factored, we don't have an x and a y both in the same factor. So let's look at the numerator. On top, both terms have a y, so we can factor out a y. Let's look at the denominator. That factor only has x's in it, so even if it did factor, we don't have to factor it because at this point there's only one variable in that current factor. Now this can be rewritten as y times 5x minus 7 over x cubed minus 5. So we have y's in one factor, x's in the other factor. So, as we've seen before, that is separable. So it's at least separable. Now, it could also be linear. So let's check to see if this one is going to be linear. So let's copy this. Put it down here at the bottom. So if it's going to be linear, then we have to keep in mind what's our linear or our independent and our dependent variable. So our independent variable is x, our dependent variable is y. So we have to have our first derivative, that's here. We have to have our dependent variable term. So let's just write this out generically. So we're going to have dy dx. We can have a coefficient as long as it's a function of the independent variable. Then we can have a y term as long as it's coefficient. And then it can have a coefficient, and it doesn't matter what that coefficient is as long as it's a function of the independent variable. And then we can have a function on the other side, but on the other side, that function has to be simply a function of the independent variable. If any of these coefficients are functions of y, the dependent variable, then it's not going to be linear. So you might look at it and say, hey, this has a y in it. That's not just x and y, so this is not linear. But things are not locked into the position that they are now. We can move things around. For example, we can move the 5xy to the other side. So if we take the 5xy and subtract it from both sides, we would get this. Since both of these terms have a y, we can factor out a y, and I'm going to put the y on the right side of the factor here, and that's going to leave us 7 minus 5x. So let's look what we have. We have our derivative, dy dx. We have our function, or our y, first power, not a derivative. And then we have to analyze and see are all the coefficients either constants or functions of x. So this coefficient is a function of x. This coefficient is a function of x. That's a constant. So yes, this one is indeed linear. dy dx, no other y's in this term. y, no other y's in this term, and a constant. Doesn't matter about our x's, what powers they're to, because they are our independent variable. So in this case, it's both separable and linear. So that's the first step towards doing what we're going to do today, is recognizing, is it separable or linear? If it's separable, then we separate and integrate. If it's linear, then we have to develop some techniques to solve them. So let's go over, well, how do we solve a linear differential equation? Page in front of it. All right, so how to solve. And this is a first order linear differential equation. So in standard form, we're going to have dy dx. The next term is going to have y, and its coefficient we're going to call p of x, and on the other side, we're going to call that q of x. So linear, our derivative with respect to y, any coefficient and any other term is simply a function of x. So here we have dy dx, here we have y and some other stuff. And what we're going to do here is we're going to try to relate this to the product rule. And you might say, product rule, what do you mean? Keep in mind that when we take the derivative of a product, we're going to have the derivative of the first times the second, and then the first times the derivative of the second. So, can we make this relate to this? When we do the derivative of this, we have one term that has the derivative of one of our factors. So here is the derivative of one of our factors. And then we have, in the other term, we have that same variable, but not the derivative of it. So what we want to do is we want to try to turn this into where the coefficient of dy dx, which right now there isn't one, but where that coefficient is v, and then the coefficient of this term over here is v prime. So we're going to multiply all three terms by some function called mu of x. It could be that at times maybe that's a constant, but often that's going to have some variable in with it. So if we think of this as being u prime v, and this being u v prime, then v prime is mu of x times p of x. And then likewise, v is mu of x. Well, if v is mu of x, if we take the derivative of both sides, then v prime would also be mu prime. So let's take this equation and let's replace v prime with mu prime. So our goal is going to be to find out what would mu need to be so that when we multiply it through, it makes this equation that we can solve. It makes it so that the left side is our derivative of a product. So that's going to depend on what our differential equation is. So P P of x, that's something we're going to know every time. Once we put our differential equation in standard form, P of x is going to be given. So let's see, can we take this relationship that we just came up with using our product rule, and can we find out what mu needs to be? So let's do this. Let's divide both sides by mu of x. So that would give us mu prime of x over mu of x equal P of x. If we were to integrate both sides, this is basically du over u, a function, the derivative of that function on top. So that integrates into natural log absolute value of mu of x. And on the other side, we've got the integral of P of x dx. Don't know what P of x is, so we don't know what the integral of that is going to be yet. But we can solve this for mu. To get rid of the natural log, we can do e to both sides. So e to the natural log cancels. So we're going to get that mu of x is e to the integral P of x d of x, or dx. So when we do that, we come up with this mu of x, which is referred to as our special integrating factor. Our special integrating factor. So then the left side now is a product rule. That left side is essentially the derivative of u times v, or in our case, it's mu times v. The right side is mu times q. So if we're wanting to solve for y, we can integrate both sides. Integral and derivative will cancel. We integrate mu of x, q of x dx. And once we integrate that, divide both sides by mu of x, and that will give us y. So let's see, how is that going to work? So that's a little bit tricky. I would encourage you to go back through and try to figure out, okay, now what did Wages just say? We're multiplying by some special integrating factor that will make the left side really product of the derivative of mu of x times y. Think about if we take the derivative of mu of x times y, we would get mu prime of x times y plus mu times y prime. So that's y prime mu. That whole thing is mu prime. That whole thing being mu prime, that's how we actually got our special integrating factor. We rearranged this, we integrated, and we solved for mu. So after we multiply through by mu, that left side is going to be mu sub x times y. Once we have mu sub x times y, on the other side, mu sub x times q. And the left side is not just mu sub x times y, it's the derivative of mu sub x times y. You might look at that and say, that's not mu times y. You're right. It's this is the derivative of mu times y. So the left side is the derivative of mu times y, even though it may not look like it. To get rid of a derivative, we integrate. To get rid of that, once we've integrated, divide by it. So let's look at an example. So to put this in standard form, we need to move the e to the 3x over. And let's even change this to plus negative 1y, because our standard form will be dy dx plus p of x times y equals q of x. So in our case here, our p of x is negative 1. Our q of x is e to the 3x. So if we would need to get our special integrating factor, mu of x is e to the integral of p. P is negative 1. If we integrate the constant, we pick up our variable, and we're not going to have a plus c for right now. Leave the plus c out here. We'll pick up our plus c elsewhere. So that's our special integrating factor, e to the negative x. So we're going to take our differential equation in standard form and multiply through by e to the negative x. So we have e to the negative x dy over dx plus negative 1 times e to the negative x times y. And that equals, on the other side, e to the negative x times e to the 3x. E to the negative x dy dx plus, we can call that negative e to the x times y. Multiplying like bases, we add the exponents, so that's e to the 2x. So the left side, we have, we could call this u prime v, and that would be u v prime. So that whole side is just the derivative of u times v. Or in other words, it's the derivative of u, which is y, times v, which is e to the negative x. So think about if we took the derivative of this with respect to x, it would be the derivative of the first part, so dy dx times the second part, plus the first part, y, times the derivative of this. And the derivative of e to the negative x is negative e to the negative x. Supposed to be negative here. So to get, we're wanting to get y. So how do we get y? We need to get rid of the d dx. So we integrate a derivative that undoes itself. To integrate the right side, if this is going to be e to the u du, if that's u, du would be 2 dx. So we divide by 2, so that would give us 1/2. And the integral of e to the u du is e to the u plus c. And then to get y by itself, we would divide through by e to the negative x. So those would cancel, and we would get y equals, we can divide each term by e to the negative x. If we divide the first term by e to the x, we have a 1/2 out front. And remember, when we divide and our exponent or our bases are the same, we subtract the exponents. So 2x minus a negative 1x, that'll make that e to the 3x. E or c divided by e to the negative x, c over e to the negative x. If we move the e to the negative x to the top, that'll make that e to the positive x. So just divide each of those by e to the negative x and simplify. All right, let's take a look at another one. So to begin with, we need to put this in standard form and see if it is indeed a linear differential equation. So if it's going to be in that form, we have to have dy dt in one term. So we need to get dy dt. So move dy over. So if we move dy over, we would have dy on this side, and divide both sides by dt. So we have dy dt on one side, and let's swap sides to make it appear simpler. Have to keep in mind what our independent and dependent variables are. So our dependent variable is y. So if we have a dy here, we also need the y term on the left side. So we'd subtract y from both sides to now give us a minus y here. So dy dt, and let's call this plus negative 1y equals t plus 1. So our standard form is, in terms of y and t, is dy dt plus p of t times y equals q of t. So that's what we have. We have our derivative plus y times some non-y coefficient, and on the other side we have non-y's. So we need our special integrating factor. So mu, this time our independent variable is t, so mu of t is e to the integral of p of t dt, keeping in mind that p of t is negative 1, q of t is t plus 1. P and q. So on the last problem we saw a p of negative 1. So mu becomes e to the negative t. So we're going to multiply every term through by our special integrating factor, which in this case is e to the negative t. So e to the negative t dy dt plus negative 1 times e to the negative t times y equals e to the negative t times t plus 1. So if we've done this correctly, then this should be a u prime and a v. And if dy dt is u prime, then y would be u, so that would be v prime. So that means the left side is the derivative of u times v, where u is y, v is e to the negative t. So again, when we get our special integrating factor, we're saying we want to make the left side the derivative of something. And if we have two terms, one of them has a derivative of y, one of them doesn't have a derivative of y, maybe we can turn that into the derivative of some product. Excuse me. So the way we came up with mu was we found out what would it take, what coefficient would we need to go with that, so that that left side is the derivative of u prime v. Again, where u prime is dy, which would make u y, and then our special integrating factor is v. So to get y, integrate both sides. Those cancel and we get y times e to the negative t equals the integral of e to the negative t times t plus 1 dt. If you want, you can multiply that out, and we can call that the integral of t e to the negative t plus e to the negative t dt. We have two terms, so we would integrate those separately. We would integrate t e to the negative t, and then we would integrate e to the negative t dt. The one on the right is just going to be e to the u du. If our exponent is negative t, the derivative of our exponent would be negative 1 dt. So pick up a negative 1 there and there. So the derivative of negative t, negative 1 dt. So e to the u du. So the integral of e to the u du is e to the u. And then eventually we're going to have a plus c there. Now the real question is, how do we integrate this? So if we look through our formulas, this would be one that we would typically integrate by parts. But instead of integrating it by parts, let's look through our antiderivatives involving e's. So here we have one that involves a variable and e to that same variable. Well, we're close to that. If we put a negative here, then this variable and that variable are the same. But if I put a negative here, I put a negative there. So this would be u, that would be e to the u, and then we would need to make that du. Well, if u is negative t, then du would be negative 1 dt, so we need to put another negative out front, so that would go back to a positive. So that's u, that's e to the u, and then that's du. So looking back, the integral of e to the, or u, e to the u du is u minus 1. So u minus 1 times e to the u, e to the u. We already have our plus c on the end. So u minus 1 e to the u, e to the u. On the other side, we have this. So we could do several things here. We could simplify the right side first. So let's go ahead and get y by itself. So if we divide by e to the negative t, those cancel. We have this term minus this term plus c. So we're going to divide each of those by e to the negative t. So we're going to have that parenthesis e to the negative t over e to the negative t. And we're going to have e to the negative t over e to the negative t. And then c over e to the negative t. So out front, those cancel. There, those cancel. So we're going to end up with y equals negative t minus 1 plus c e to the negative t, or c e to the positive t when we move that up. So this would be minus t minus 2 plus c e to the t. Biggest key here is finding that special integrating factor, mu sub x. In linear first order differential equations, mu is always going to be e to the integral of p. Whatever we determine p to be, mu is going to be the integral of p, e to that. So when we multiply everything through by the integrating factor, this left side can be written as the derivative of two things, a product. The derivative of what? We have y and y prime here, so y is one of them. And then if this is y prime, this is the other. Get rid of the derivative, integrate both sides, and go from there. So let's do one where we have an initial value. So we need to begin by rewriting this one. So our independent variable is t, our dependent variable is x. So if this is going to be in standard form, we want to divide everything by t squared. So those cancel, giving us dx dt. That t and that t reduce, leaving us a t on bottom. And remember that x is our dependent variable. So if we have a dx dt here, we need an x here. And then we can call this either 3 over t or 3 times t to the negative 1, either way. So I'm just going to write it like this. X times 3 over t. On the other side, we get a t squared natural log of t plus, let's call that t to the negative 2. This is our dx dt. This is our p of t times x, and this is our q of t. So p of t is 3 over t. So mu of t is going to be e to the integral of that, 3 over t dt. If we put the 3 out front, then we'll have the integral of dt over t. So this is e to the 3. The integral of dt over t is natural log absolute value of u. If we have e to a natural log, those cancel. But we can't have a coefficient out front when that happens. So that 3 needs to go up front. And I don't know why I'm putting u there. Our variable is t. So this is t here. So if we rewrite this, mu of t is e to the natural log of t cubed. That goes up to the exponent. And now that we have e to the natural log, those undo each other, giving us t cubed. So a big part here is making sure that when we integrate, we don't cancel these out until the 3 goes up as the exponent. All right, so now that we have this, we multiply our differential equation that was in standard form by our integrated factor. So we have t cubed dx dt plus 3 over t times t cubed times x, and then we're going to multiply the other side by t cubed times t squared natural log t plus t cubed times t to the negative 2. So each term we're multiplying by t to the third. T to the third, t to the third, t to the third, t to the third. So we get t cubed dx dt. That reduces, and that gives us 3t squared times x, t to the 5th natural log of t. Add those exponents, and that would give us t to the 1st. For this left side, if we've done this correctly, this is the derivative of some product. So the derivative of what product? So x is one of those, because here's, if we call this u prime, and this v, then this would be u, and that whole thing would be v prime. U prime, v prime. And that looks correct. If this is u, the derivative of that is dx dt. If this is v, the derivative of that is 3t squared. So yeah, so u times v. Once we get here, we need to integrate both sides with respect to t. So those cancel, giving us x times t cubed. On the other side, we have two terms, so let's integrate those separately. Let's integrate t to the 5th natural log of t dt, and then let's integrate t dt. So the integral of t, that's just t squared over 2, and we can go ahead and put our plus c in. This integral is an integration by parts, so let's go to the table for it. So do we have one that involves our variable to a power and natural log of that? So here, look, here we have some natural logs. Here we have natural log of a variable, and then our variable to that power. to some power. Notice that's what we have here. Here's our variable to a power, and this is the derivative of our variable. So that integral is going to be our variable to the 1 greater power. So our variable to the 1 greater power over that same power squared. So that same power squared. Then that's times -1 plus n plus 1, and n plus 1 is what our exponent was, which is 6. That's times natural log of our variable, and then plus c, and we've already got a plus c. So our variable to the 1 greater power, over that power squared, -1 plus our power, our new power, times natural log t. So x times t cubed is, we have t to the 6 over 36. And we could, we could go ahead and multiply this out. So if we multiply that times -1, that would be negative. If we multiply that times here, this 6 will cancel with one of those 6's, so that'll give us t to the 6th over 6 natural log t, and then that's not distributed to the other terms. So this term, the 6, and one of those 6's reduced. We're wanting to get x, because x is going to be a function of t, so if we divide everything through by t cubed, we get minus t to the 3rd over 36 plus, these reduce, so t to the 3rd over 6 natural log of t plus 1 over 2t plus c t to the -3, or we could call that t cubed on bottom, or we could call that t to the -1 on top. Only thing left to do is that when we put a 1 in, we get a 0 out. Our input is t, our output is x. So to find c, if we put a 1 in for t, we get 1 cubed, so 1 over 36, plus 1 cubed, so 1 over 6 natural log of 1, plus 1 over 2 times 1, plus, we said we could call that t cubed on bottom, so c over 1 cubed, and that should equal 0. When t is 1, x is 0. Natural log of 1 is 0, so that's gone. So we have -1 over 36 plus 1/2 plus c equals 0. So c is 1 over 36 minus 1/2. 1/2 is also known as 18 over 36. So -17 over 36. So that's c. We just took this and got c by itself. So our solution to our initial value problem is -t cubed over 36 plus t cubed over 6 natural log of t plus 1 over 2t plus c, and c either has t cubed on bottom or is times t to the -3. There's our solution.